Okay, everyone. So today's last speaker is by Professor Alice Tan from Princeton University. She will talk about on a problem of conformal filling in by Poincare Einstein matrix.
Okay, so let me first thank the organizer for inviting me. It's a true pleasure to be here and meet many acquaintances, old and new. Okay, so I will save my remarks for 10 later in the dinner. So now let me begin by explaining the title of my talk. So what I call conformal fill-in by Einstein manifold is the following. Suppose I have a manifold MNH, which is a boundary of a conformal compact Einstein manifold. I will specify more later. And that's Xn plus 1 G plus. And G plus is Einstein. And then G plus itself is non-compact and blow up near the infinity, near its boundary, for example, hyperbolic space. But I can get a defining function, rho square G plus, which restrict to the boundary is H. And then in this case, we say this Xn G plus is a conformal filling in of the original manifold, MNH. This is a problem that occurred in this ADS conformal field theory and first proposed by Mendocino and Wheaton. And of course, in geometry, we also have a lot of study of such space because this space is a special case of asymptotic hyperbolic manifold. So more specifically, I mean the following. First, on a manifold, I have a defining function, rho. And that means rho is positive on X, and d rho is not equal to 0 on manifold. And then it's conformally compact, means itself is not compact, but I have such a defining function, rho squared times G plus, it becomes compact. And because the choice of this defining function rho is by no means unique, once you have one, you can multiply it by another function, and it's still conformal, is still a defining function. So this H is decided up to conformal class, multiple positive function. So I have this H. And then I say it's a Poincare Einstein filling in if the inside Einstein is actually Poincare Einstein. Okay, and so we call it a conformal compact Einstein filling in. And one remark is for such filling in, there is a special defining function called geodesic defining function. This geodesic defining function makes this near the conformal infinity, the metric almost like a product metric, R squared G plus. But the problem is this defining function usually is defined on an asymptotic neighborhood in a very small neighborhood. It's not defining on the whole space. So that's a geodesic defining function. So let me talk about a couple examples. The first example is just the upper half space with hyperbolic metric. And in this case, the geodesic defining function, of course, is y, the distance function y. And y squared GH plus is the upper half space. It's not compact. So it's not really a CCE, but this is always the blow-up limit of a CCE manifold. And whenever we try to prove something, and we are trying to get a Liouville theorem on this limiting case. So a real example is the hyperbolic ball. So there is this ball hyperbolic metric. And in this case, the defining function is this function, 1 minus y over 1 plus y. And if we times this defining function, and when R is restricted to the boundary, then R squared G plus, when R is equal to 0, is this canonical metric on the sphere. So sphere is the conformal filling in of a hyperbolic ball is the conformal filling in of the sphere. And actually, there's a very interesting and important example, and that's the case when your boundary is S1 cross S3, S2, okay? It could be S1 minus 1, but the S1 lambda cross S2. And in this case, it turns out, depending on the size of lambda, there exists at least 3 different types of filling in. And the first type is you begin to develop S2 and compactify it by Einstein H3. So it's the B3 equipped with hyperbolic metric, and then S1 stays the same, and you take the Y product. In that case, this is a hyperbolic manifold, and this one exists for all lambda. But it turns out there's other way of filling in, and that filling in is you develop S1 by B2 or S1 by R2, and then cross S2. And in that case, and that's the example of ADS Schwarzschild space, and it turns out a very amazing result that when lambda is sufficiently small, then for the same lambda, there are 2 different choices of the max and make this conformal compact Einstein filling in. So the picture we get is, given a boundary, there may be different topology to filling in. And even if with the same topology, there may be different filling in, different conformal, by no means unique. And now let me talk a little bit of certain early existence result. I'm just choosing the one which is related to what I want to talk about later. And the first one is the important filling in of Grant and Lee, saying if you perturb the standard metric Sn, then in a small C2 alpha neighborhood, you can have a filling in. Okay, so in this case, there is also the example that on Sn with canonical metric, Qingjie has an early result saying that hyperbolic ball is the unique filling in. And it turns out that even in this neighborhood, one can show that the filling in constructed by Grant and Lee is in a neighborhood of hyperbolic metric, and that's also the unique one. Okay. And then on the other hand, there is a non-existence result. The non-existent result, I'm talking about a special case of it, and that is on B8, say X4K, say K equal to 2. You talk about B8 with S7 as conformal infinity. And what their example is, on S7, you can have a metric which is with positive scalar curvature and which does not allow a conformal filling in. Okay, and I will not go into detail, but let me say this result used 2 important facts in this field. And one is a result of Jack Lee, which says if the scalar curvature on the boundary is positive, then the first eigenvalue of this Poincare-Einstein metric is greater than n squared over 4. And this theorem also has an important observation by Qingjie. Qingjie later observes that the proof of Lee actually shows that if the boundary has positive scalar curvature, then you can construct a compactification inside, which also has positive scalar curvature. Okay. So I probably will skip this page. So now, given this example and counterexample, an open question, still open, is because the example of Gursky and Han is for dimension 4k, k must be greater than 2. So on B4, we ask what happens if on B4, suppose we have on 3 sphere with a positive scalar curvature. In that case, one knows that the class of path-connected metric on S3 is one component, and on S7 there are multiple components. So the example argument of Gursky and so on does not work. So it's still an open question. Does the entire class of positive scalar curvature on 3 sphere allow a conformal filling in? We did not answer this question, but first let me formulate a corresponding compactness problem. We know that the problem is not only you have existence problem, but you may have uniqueness problem of the extension. So it makes sense to first handle the compactness problem. The compactness problem I formulate this way. If suppose I given a class of boundary metric, and which in a conformal class, the moduli class, is a compact family. And suppose I know this HI has filling in GI, okay? And then I GI plus, and then I compactify it. I ask, does this compactify class, the modular class is compact? Okay, so we ask this compactness problem. Okay, so now let me say what is the difficulty of answering this compactness problem, one of the difficulty. And let me restrict
刘雷，你先别弄呢，
four manifold boundary.
我这听东西呢。
Okay, so in this case,
你待会儿吧。
Say that again. Okay. So in this case, there is this asymptotic expansion
你过来看一眼。
of compactification.
我说你过来看一眼。
The first term is dr square. The second
这
term
不
is
田刚那个会吗？就是那就是 Alice Chang， 就 Princeton 的老
and then
会。
you have r square and
见过。
r cube.
哦，我见过，对啊，嗯。
76了还是？
嗯。
Okay, so okay, so there is this asymptotic behavior. And it turns out this G2 is just the curvature of the boundary edge. So I call it a local quantity. It's decided by the boundary. And then the G3 turns out to be the sum of the Ricci curvature of the tangential derivative DD normal. The tangential part of the Ricci and then normal. So that's a non-local property. It's like the Dirichlet to Neumann problem. This G3 is not determined by H. Okay. So the question is, now G3 and H altogether decide G. But on the other hand, this G3 is not decided by H. So our question is really, suppose I know H already allows CCE filling in, does it decide this, what's the control you have about G3? Okay, what's the behavior of this non-local quantity controlled by this boundary information? Suppose you already know there is a specific structure inside. Okay, and so for this problem, For this problem, we now have this conformal problem. So we want to study conformal filling in. So we want to control constants which are conformally invariant. A well-known constant is the Yamabe constant on the boundary. And let me say that analytically, this means you control the isometric embedding constant from W12 to L2n over n minus 2. And then for manifold with boundary, turns out there are two such invariants. One is this normalized volume and scalar plus mean value. The other is you normalize the boundary volume. Okay, so there is two constant, one called one YA, YB. So our first result, first observation is what Qingjie says, the result says is if the boundary is positive scalar curvature, that implies the boundary Yamabe constant is positive, then the interior Yamabe constant must be greater than equal to 0. Okay, must be greater than equal to 0. But it turns out one can quantize that argument to say, actually, if the boundary Yamabe constant is bounded away from 0, then the interior is bounded away from 0. So that's this first inequality. And it turns out, so is the Sobolev constant, YB. If you are allowed a CCE, then YB also is bounded from below if the initial Yamabe constant is bounded from below. And these are work of a group of people. Okay, so let me not, in particular, the result of Chen Lai and Wang Fang have the sharp constant. Okay. It seems I missed one page. Okay, sure. Okay, and then the other conformal invariant is the Weyl curvature. It turns out Weyl is a pointwise conformal invariant. So Weyl Ln over n plus 1 over 2, the integration is an invariant. And then, for example, when n equal to 3, we talk about Weyl L2 no. And so the Bach tensor is the critical point of Weyl tensor. So that's a pointwise conformal invariant. And so this Bach tensor, the space of Bach flat metric, has been studied by Tian and Vyakovsky. So we are inspired by their work. And one observation is, in the case of, one can rewrite this Bach flat condition into an elliptic system. And that elliptic system is Laplace Ricci plus this Rn convoluted with Ricci, and except there is this Hessian scalar term. And if one look at this fourth order elliptic PDE, this is matching very well with the local term G3 we try to capture. It's a natural system. So we have this interior, this boundary. Okay, and now we try to formulate our compactness result. We want to do things in a conformal class, so it depends on what is the conformal representative you are choosing. And on the boundary, it's very easy to think about what's the most natural representative. That's the Yamabe metric. And one can also say in the interior, which is the Yamabe metric too. But the problem is, once you do that, the interior Yamabe metric, when it's restricted to the boundary, no longer is the boundary Yamabe metric. So you lose control of its boundary behavior. So instead, what we do is we need to do the construction by giving an edge and choose a conformal invariant, choose a compactification inside. So we have good control of the behavior of it near the boundary. So in that case, we have a choice. Let me not go into detail. The choice by solving this type of a scattering metric, scattering theory, and choose a representative. And the representative we choose turns out to be related to the index 1/2 + 1. And that representative has the good property that it's scalar flat and its mean curvature positive. So in summary, given a boundary metric, suppose I know it's already a CCE, I have a good representative with mean scalar equal to 0 and mean equal to mean curvature positive. Okay, so the first result we have is, we have some early result, but the first result, which is stated completely into conformal invariant, is this result. Suppose we have a boundary class of metric HI, which is compact, boundary compact, Yamabe constant bounded from 0 away from 0, and mean curvature, the via L2 norm is bounded, uniform bounded. So these two conditions turns out prevent this sequence of adapted metric, compactified adapted metric from to have boundary blow up. But we also need some condition to prevent the interior blow up, and that's this topology condition. Under these three conditions, we have compactness. So that is the boundary constraint implied the interior metric is compact. Okay, and now I want to briefly describe how to application of this result. So first, we know that the original metric, if H is in a perturbation result, then you know the via curvature, the L2 norm, has to be very small. But on the other hand, in her early work of Wang Fang, she already observes that for the linearized Einstein equation to have no kernel, you only need the condition via L2 norm less than a multiple of YA if the boundary metric has positive scalar curvature, then you avoid the kernel. So in other words, if this H you already know is interior has satisfied this condition, then in the neighborhood of that H, you also have a conformal filling in. Okay, so our task is now trying to see if there are any condition on the boundary H so that forces this star to always hold. Okay, so that we can have openness and we can use continuity argument. The existence result we have is the following. Indeed, this is the case. So suppose we have B4S3, and suppose we have an H metric on the boundary S3. I need to assume that this C4 bound, and then assume the volume is 1. And then I need to add an additional condition. The additional condition is the traceless part, traceless receipt part of HL2 norm on the boundary is small. But that small is a definite number. It's not asymptotic small. So that this number times this a constant depending only on this C4 bar and delta is less than 1/4 of the Yamabe metric. In that case, the YA is also bounded from below. So if it's less small, then I push the existence of YOL2 norm satisfy this. So, and also in that case, we get this H has a CCE filling in, and within this constraint, that's also unique. So the difference of this result with the previous result is we now have a definite size of vial. Vial, it does not need to be asymptotically small. It only needs a fixed positive number, small, and then it has a filling in. Okay, so let me briefly outline the proof of the existence theorem. So there are 3 steps. First step, so I denote this the local quantity G3 by S. So the problem is how to control S under our boundary constraint. The first step is using this Bach-Flat equation to say that this term, a multiple YA minus vial L2 known, and then vial L4 known. That together, if one look at that, that's bounded by the boundary integration of S and E hat. E hat is a boundary condition. So to control the growth of this, I need to control S. And S is a local quantity. How do we control it? And step 2 is to say, yes, indeed, if this constant is positive under similar condition of that, we can control the SL3 node, and that's bounded by some number. Okay, and this is a step I will fill in later. This is the critical step. And combining this, suppose I also have E hat 3/2 known sufficiently small, then I can bring the L2 known of vial under control. And that finishes the proof. But how do we do that? So it almost looks like you start with this assumption, and then you get similar result. You say, I start with assume this, and will get something similar. But that's actually not the case. What it says is, if you start somewhere where this condition is true, and then you continue your path, and then in the end, you still fall in that channel. So you get the existence. So in that case, we need a continuity argument. So the continuity argument is, I now connect H to the original HC. Remember, I'm on S3. So at the beginning, I have the double star condition, and we try to connect a continuous path. So the condition I put on is, in this family, continue to be true. And luckily for us, we found that in the recent work of Guofang Wei with Eric Chen and Rugang Ye, this is a special case of the result, saying indeed, on S3H, if you start with something, their assumption is a little bit different than us. But suppose the scalar is positive, then L3 norm, if it's small, then along the Ricci flow, it converges uniformly in any topology. As if you assume H has C4, then it's in C4 topology down to HC. So applying the result, we can connect the path. And in our original assumption, we assume this E hat H L2 non small, but it turns out this small implies that small in 3 dimensions. Okay, so in 3 dimensions. So that's the condition. So now I have 1 minute, but let me say, maybe I borrow 2 minutes because we stop in the time. I'm saying that how do we control this S tensor, the norm, the DD normal, the third derivative norm? And the idea turns out comes from the early work for Bendo, Kasu, and Nakajima. And they study this asymptotic ALEN of sequence of vial curvature with Einstein manifold. And they made a crucial observation that for Einstein manifold, metric vial has this Carter constant 5/3. And that leads this vial 1/3 to satisfy a decay property of the equation. That means minus Laplace of function v less than equal to some fv plus something, and this f is in Ln/2. And in this case, it's 4 manifold, dimension d/2, d equal to 2. And so there is this vial and 1/3 condition. And so using elliptic PDE, they get vial decay and passing the order of 1x2 minus, so vial plus is actually 1x6, and that's more than you need for the ALEN behavior of the vial. So what do? We try to translate the result to the conformal setting. So it turns out if you consider this metric rho square G plus, then the corresponding thing instead of vial to the 1/3 is vial over rho. And if one consider that, one get an elliptic PDE minus Laplace U of this. So you anticipate this U have good behavior near the conformal infinity. Okay, and that's indeed the case. So based on this PDE, which is the analog of this Einstein case, we begin to study the behavior of U, and which is reflected in the following thing. If you look at the vial L2 norm, if you expand it out, and then you can see the R vial is equal to 0 on the boundary, and the R square term has E2 has S tensor, DD normal appearing. And its normal derivative, the E cubed term, has S times the Curtin tensor and the normal the derivative. So this is hat means boundary behavior. So it's S this. So if we use this, and then our early knowledge of U6, then you know very well the U6 boundary behavior and U6 normal derivative behavior. And using that, coupled with our knowledge of, we control the Sobolev constant, isometric embedding the isometric constant, and then this trace Sobolev constant, YA, YB all have lower bound. You use the information combining in with your estimate. I'm sorry, I'm rush. And then what you get is this estimate. You have S L3 known square. And then on the right-hand side, you have S times the Curtin tensor, the leading order term. So the offshore is S3 L2 square term bounded by this S L3 known times the information on the boundary. And that's the crucial estimate. And since we know YA, YB already have a lower bound, so we get the bound we want. So, and that's the key point of this approach. So, that I finished my talk. Say happy birthday, Tiangang. May your future years be as productive as ever. Thank you.
Okay, any questions?
Alice, so maybe I ask a question. So this, I guess in your talk, this L2 normal for W, YU tensor is plays a very important role. Is there can L2 normal of W bounded by this H boundary value and G3
Yes.
maybe?
Yeah, that's exactly the problem we are working on, and I'm keep on bugging Aaron neighbor for help to see that if there is a boundary condition on H which already make the vial L2 norm bounded.
I see.
So yeah. So if that's true, we believe we have a degree theory. We have a degree theory for this linearized Einstein equation. So, but that's the difficult part because in the work, we only need a vial L2 norm for the boundary blow up. For the interior blow up by the work of Chigger and our neighbor, the vial L2 norm is automatic. So that seems to indicate maybe this condition can be controlled other way, but we don't know. We don't know.
Thank you.
Yeah.
Thank you.
Any other questions?
Yes.
A lot of these spaces in your constructions are similar to the construction of universal Teichmuller space. And I was wondering, for example, the conformal group of the Poincaré space is in one of your examples. And I was wondering if you had any way of tying this in or have thought about if that would be relative to any of these constructions.
No, we haven't. We have studied in separate work, we have studied this S1 lambda cross S2 case, but we haven't studied general cases.
I see, okay.
Yeah.
There may be some big space for all your examples to live
Yeah,
in somewhere.
could be, but
Could be, right. We don't know yet.
we are staying on S3 at this moment.
Stay well grounded, huh?
Yeah.
Thank you.
Yes.
Do we know about the behavior of a capital U at infinity? Capital U?
Capital U?
Yeah.
Yes.
Yeah.
Do we know?
Do you know about the behavior of a capital U at infinity, conformal infinity?
No, we don't. Because the behavior of U involving S, this S is unknown. So in early work, we assume S equal to 0, and then we can capture the behavior, ALEM behavior of U. But because the S norm comes in, and the difficulty of this S norm is L1 invariant. Suppose I assume S is an LP property, P bigger than 1, then I have good control. But I only have, for this problem, I try to control quantity which are conformally invariant. And then S is L1 invariant, so it's very hard to push behavior. If I assume S is in LP, then we have some control of the behavior of U at infinity. Yes.
Okay, any more questions? Okay, if not, let's thank Professor Zhang again for inspiring talk.